Welcome to section 11.1 and 11.2, where we talk about the chi-square distribution. The chi-squared distribution is notated x is distributed chi-squared with df degrees of freedom. That value right there that is underlined looks like an x maybe, but it's actually the Greek letter chi, and it's chi-squared for this distribution. It uses degrees of freedom like the student's t distribution does. I just realized that this is not spelled correctly. Distribution, typo there, sorry about that. The population mean is mu equal to the degrees of freedom, and the population standard deviation is sigma equal to the square root of 2 times the degrees of freedom. Let's take a look at what the chi-square distribution looks like. Here's its graph in Desmos, and this one is set to 1 degree of freedom. And it looks almost like an exponential curve. As you move the degrees of freedom up, the graph starts moving towards the right, and it starts to be more and more shaped like a normal distribution. Remember, the mean is equal to the degrees of freedom, so right here is the mean at 6, just kind of sitting to the right of the peak of the curve. As you move it out, it gets more and more shaped like the uniform distribution. Normal distribution, sorry. As you move the degrees of freedom out, its shape is more and more like a normal distribution. Couple just facts to remember: it is non-symmetric, which you could see, and it is skewed right. The mean is always located just to the right of the peak, and it approximates a normal distribution as the degrees of freedom increase. All right, so we're going to jump right in and do a goodness of fit test, which is what we use the chi-square distribution for. One of the things we use the chi-square distribution for. A goodness of fit test is used to decide if data fits a particular distribution or not. So we think we know something about some data, and we're going to decide if this data matches it or does not match. For example, we might think unknown data should match particular expected values. And we're going to use this chi-square test to determine if the data fits those things that we expect or not. A goodness of fit test looks at the difference between observed values from the data and what you would expect given the underlying distribution, or what you think is the underlying distribution. Here is the test statistic that we're going to use. We are going to calculate this using our RSubEDI online calculator, but we're going to do it by hand as well. O is going to be our observed values, E is our expected values from our theory of what we think is going on, and K is the number of different categories. So we're going to sort of sum up the difference between what we expect and what we observe. Let's go ahead and give this a try with something that's pretty straightforward to understand. We have a 6-sided die, and it's rolled 120 times, and it gives us the following results. Our question is this a fair die, or maybe is it a loaded die? So we look at the data, it's kind of hard to judge. 2 and 5 both have higher values than the other ones, but is it high enough to be significant? That's the question that we're going to answer. So let's go ahead and state the null and alternative hypotheses. For the goodness of fit test, the null hypothesis is always going to be that the observed values fit the distribution, and that the alternative is going to be the observed values do not fit the distribution. So in this case, the null hypothesis is the dice is fair, and the alternative hypothesis is the dice is not fair. I sort of think of this as this is a dice is equal to fair, the dice is not equal to fair, and we always have the equal sign in our null hypothesis. So our null hypothesis is the assumption that this does fit the distribution we think it does. We think it's just a fair die. Well, now what we need to do is we need to compute what we would expect the frequency to be if the dice was fair, or if we assume the null hypothesis is true. Remember, dice is binomial with n equal to 120 and p equal to 1/6 for each of the 6 values. So we expect about 120 times 1/6 for each of those, which is conveniently 20. I set it up that way. So if we rolled a dice 120 times, we expect to see about 20 of those to be 1s, 20 of those to be rolled 2s, etc. So what we're going to do now is we're going to do some computations. We want to get finally to this last column, which is O minus E squared over E, but by taking steps at a time, it goes a little bit more smoothly. The first thing we're going to, I did not mean to bump that. The first thing we're going to check is just the difference between the observed frequency and the expected frequency. So in this case, this is 15 minus 20, which is negative 5. Just like when we computed variance, we want to square these because we don't want the negative ones to cancel out with the positive ones. So the next thing we do in this column is we square those values, O minus E. So we're going to square negative 5 to get 25. And the last thing we do is we take that squared value and divide it by E. So in this case, this is 25 over 20. Our expected value here is 20. Our O minus E was 25. 25 over 20, can't grab my handy dandy calculator, is about 1.25 exactly. Why don't you pause the video and calculate the second row? All right, are you back? Well, let's take O minus E. That's 29 minus 20. In this case, is positive 9. O minus E squared is going to be 9 squared, which is 81. And O minus E over E is 81 over our expected value of 20, which is 4.05. We're going to continue doing these calculations for all the different values. Why don't you pause the video and do all the calculations right now? All right, are you back? Did you get the same thing that I got? Hopefully you did. Now the last part that we're going to do is we remember that our test statistic had a summation sign in over all values of K. K is the number of categories that we have. In this case, we have 6 categories for 6 sides of the dice. We have all our O minus E squares over E right here. And to get our test statistic chi-squared, we just add them all up. We add them all up and we get 13.6. That's the value of our test statistic. I feel like this is out of order. Oh, never mind. I'm sorry. I just blanked at it for a second. All right. So the value of our test statistic is 13.6. We're going to use Desmos to help us calculate what that probability would be. Let's go ahead and go to Desmos. All right. So what was our degrees of freedom? Remember, that was 1 minus the number of categories we had. So in this case, it's going to be 5. And the value of our test statistic is, what was the value of our test statistic? 13.6. So we put in 13.6 for our test statistic value, and we get a p-value of 0.01836, right? So if you zoom in, you can actually see there's our 13.6, and there's the area under the chi-square curve that is bigger than that. So that's going to be, that area is equal to the p-value, which is 0.01836. Here's where I have that information shared. Let's get this going again. Again, the same, the degrees of freedom are 1 less than the number of categories, so in this case that's 5. The value that we computed from our table was 13.6, the value of our statistic, which gives us a p-value of 0.01836. This does seem like a lot of computations to do in the year 2022. So we're going to use R sub Betty to do this as well. However, it is important to note that R sub Betty has a few limitations on this and the number of values you can type it in. So I thought it would be really useful for you guys to know how to do this by hand and computationally. By hand, it really isn't that difficult. So we go to R sub Betty, and it will look like this. We go to chi-square tests under hypothesis testing. We choose goodness of fit, and we put in our data, our observed value and our expected values. Now, again, you have to come up with your expected values. The calculator is not going to come up with that for you, and that requires your understanding of, in this case, the binomial distribution and expected value of phi. So we put in all our values and we hit calculate. We came up with the same test statistic, so that's encouraging. We came up with the same p-value, which is also encouraging, and we had our degrees of freedom, which was 1 less than the number of categories. So the probability of getting this frequency distribution with a fair die has a p-value of 0.0184. We weren't given a significance level, so of course we assume alpha to be 0.05. The probability of this occurring is less than our significance level, so the null must go. So our decision is to reject the null hypothesis. The null hypothesis said this was from a fair die. The alternative hypothesis says this was from a not fair die. So the data does not support that this is a fair die at the 5% significance level. All right, let's try another example. This one's a little bit more a little bit different. So what we're going to do now is we're going to test to see if a population is fairly represented. The column below contains the race, ethnicity of a U.S. public school and overall student population. A local school has 1,000 students, and we want to see if their distribution of students matches that of overall student populations at U.S. public schools. So in this column, this is what data that we got from U.S. public schools. They say that in all the U.S. public schools, 5.4% of the student population is Asian. This column is from the survey of 1,000 students at a local school. Okay, so this column is this is the survey frequency, and these are the results from the survey. We're going to see if these results match up with our overall student population. So, of course, step one, as always, is to state the null and alternative hypotheses. So the null hypothesis is always going to be that the distributions match. So the local results match the distribution of overall U.S. public schools is our null hypothesis. Our alternative hypothesis is they do not match. The next thing what we need to do in this one is we need to figure out what would we expect if they did match, okay? So this is the data from before. Remember, this is from our survey. So we're going to ignore this for now. And what we're going to say is, remember, it was 1,000. Oh, my goodness. I bumped that thing again. It was 1,000 students that were surveyed. We have to do a little bit of arithmetic here. If we expect 5.4 of 1,000 to be Asian, that means we're going to take 0.054 times 1,000. And that's the expected number of students in our 1,000 student population that should be Asian. So our expected value is going to be 1,000 times 0.54, which is 54. And that's where we get this value here, right? 14.5% of 1,000 is 145. 15.9% of 1,000 is 159, and so on. So these are our expected survey frequencies based on the fact that we had 1,000 students in our population and these given percentages for overall student population that we're assuming is the true distribution of students, right? So again, this middle column, this is from our sample data, right? This is what we actually observed. This column is what we expect. I didn't mean to outline, cross that out. I was meaning to underline it. Gosh dang, I'm having a hard time today, aren't I? This is what we are expecting to happen, okay? So this is from our computations based on the overall student population times the number of students. So what we're going to do is we're going to compare these two columns, what we actually observed with what we would expect to observe. We're going to use the calculator this time. There are 6 categories again, so we use 5 degrees of freedom. This is just a coincidence. There is not always 5 degrees of freedom for this type of a test. We just happen to have 6 categories again. We put in our goodness of fit choice. We put in our observed values and our expected values. It's very important that you have those in the correct columns, and we hit calculate. Our chi-square test statistic value is about 9.1. Our p-value is 0.10566, and our degrees of freedom are 5. Again, this was just a coincidence. It's not always 5. So let's look at our p-value. The probability of getting this frequency distribution, assuming the student population is given by that data, the U.S. distribution, is about 10.6%. This is higher than our default alpha of 5%. So our decision in this case is to accept the null hypothesis. Not that unlikely we would have this distribution. Could happen 10% of the time at random. So our conclusion is that the data supports that the students at this local school do follow the overall distribution for U.S. students. We should probably say at a 5% significance level. All right, well, this is section, I forgot I included a graph just because I like graphs. So here is our chi-square test with 5 degrees of freedom. Here is where our test statistic ended up at about 9.08. That was our test statistic. And here would have been our cutoff. This is our rejection region. We didn't fall in the rejection region, so we didn't reject, and we accepted the null hypothesis. I just include this because I like looking at the chi-square graphs. All right, that's all I have for 11.1 and 11.2.